Okay. I'd now like to introduce our moderator, Amy Merkel. Amy is a LASP scientist, and she is also the lead of our Office of Communications and Outreach. Amy?
Hi, everyone. Thank you so much for joining our first webinar in our series, fall series. It's my pleasure to introduce Dr. Gary Rotman. Dr. Rotman has had an amazing career and was instrumental in LASP playing a major role that it does in NASA's effort to continually monitor the energy from the sun. His initial efforts have now paid back tenfold by the SORCE mission producing the longest continuous solar data record from a satellite. Dr. Rotman received his PhD in physics from the Johns Hopkins University in 1972, and shortly after joined the research faculty at the Laboratory for Atmospheric and Space Physics at the University of Colorado. He took a short break from LASP, and from 1992 to 1996, he was a senior scientist at the High Altitude Observatory at NCAR. He returned to LASP in 1996 and was a senior researcher for another 9 years before he retired in 2005. His primary research focus was on the development of ultraviolet instrumentation to study the Earth's atmosphere, the sun, and its planets. Over the course of his amazing career, Dr. Rotman contributed to more than 25 sounding rocket experiments. He was a co-investigator and project scientist for the highly successful Solar Mesosphere Explorer. He was the principal investigator for the SOLSTICE instrument on the Upper Atmosphere Research Satellite called UARS, and was a co-eye on the TIME-C and SDO-EVE experiments. Pertaining directly to this talk, Dr. Rotman was the original principal investigator of NASA's SORCE mission, which launched in 2003 and was recently decommissioned in February of this year, which provided 17 years of solar measurements. Dr. Rotman directed the development, launch, and early operations of the SORCE mission until his retirement in 2005. Dr. Rotman has remained active in the solar science community and has special interests on how the sun, as the primary energy source to the Earth's atmosphere, affects our climate. Thank you, Dr. Rotman, for being our first presenter in our fall webinar series. I'll now give the presentation screen over to you.
All right, thank you very much for the introduction. I'm very pleased to be here. Here, meaning in Durango. I'm going to now start sharing my screen. And yes, please bear with me. We can do this. So there you have it. There's the Solar Radiation and Climate Experiment, launched in 2003 and decommissioned February of this year. I am now retired. I am down in Durango, Colorado. That's where this webinar is coming from. I didn't mean to do that, pardon me. Let me go back. Somehow I'm not seeing my full screen, but anyway, down at the bottom of my screen, I don't know how much else will be missed, but I have my web address, my email address, and if you have anything to complain about at this talk, then you should email me, but evidently you won't have that address. So here's what LASP does very well. It thinks up scientific endeavors to pursue. That's what the scientific staff does. We have a wonderful engineering group who builds instruments, mechanical engineers, electrical engineers, test engineers. And these are the 4 instruments that are on SORCE. They all have names: TIM, the Total Irradiance Monitor; SIM, the Spectral Irradiance Monitor; SOLSTICE, the Solar Stellar Irradiance Comparison Experiment; and the XUV Photometer System. They are all put together on part of the observatory on this optical bench. I call this Postcards from SORCE. So here are the 4 instruments, and actually the SOLSTICE is 2 instruments that are set up orthogonal to each other. And then I think I have to do those arrows. So we then ship that observatory off to Orbital Sciences, who are just north of Dulles Airport in Virginia. They built the spacecraft bus. We married the observatory to the spacecraft bus and did all the testing here at Orbital. And then that truck, that United truck, is taking the whole satellite and payload down to the Kennedy Space Center. And here we're in a big clean room area, and this is the Pegasus, the launch vehicle, and then a clean room on the end. And in the clean room is where the satellite was put together inside the fairing and then prepared for launch. I don't have the best pictures of the launch, but the launch happens that Pegasus is strapped to the bottom of this L-1011 aircraft. It flies up to about 40,000 feet, does a bit of a dive to gain speed, and then it drops the Pegasus from underneath. And the Pegasus just free falls for 5 seconds, and everybody holds their breath. And then the Pegasus lights. Now, this is not one picture of that. As you can see, the Pegasus is still on the bottom of the aircraft, and there it goes. But you get the idea of how this happens. And soon the satellite is in orbit. Then the other part that LASP does is it has a clean room, or not a clean room, a control center, also on campus in Boulder. And here you see some professionals and students who then begin to operate the spacecraft. This is one of the tools they use to plan, send commands, and of course then the data comes back to the control center, is distributed to the scientists, and they proceed to analyze the data and publish papers. So here's an outline of the talk, and the first thing is a brief introduction to SORCE, and you've just had that. That's the brief introduction. But then I would like to talk a while about the science of optics. The subset of that is spectroscopy and how LASP uses this to do remote sensing, not only of these irradiance solar measurements, also planetary science, upper Earth atmosphere science, and even very distant astrophysical objects. And you use spectroscopy to do this. I will talk about that a bit because after speaking to that, at the end, we'll come back to SORCE, and hopefully some of the instruments, it will make more sense. But I also want to talk about the sun's effect on the Earth's climate, on the Earth's environment, but in particular in this case on climate. Now, I'll very briefly review the LASP irradiance program, which began in 1972 up to the present time. And then, like I said, we will go back to SORCE, revisit the instruments, and see how this is done. Now, I don't know for this webinar, I know it's a public lecture. I don't know what everybody's background is, and I'm sure they're all different. I've lost my control. So I hope this isn't too watered down, but by the same token, I hope it isn't over people's head. So first of all, light. Light is electromagnetic radiation. It comes in the form of photons. Associated with them is a wavelength. The inverse of that is a frequency. The photon itself has no mass. That just means it's not affected by gravity. It has no charge, so it's not affected by electric and magnetic fields. It just shoots in a straight line at the speed of light, 300,000 kilometers per second. And this is a little cartoon schematic of the electromagnetic spectrum, and I doubt that you can read the wavelengths. They're in centimeters, but it doesn't matter. To the left are very, very short wavelengths, meaning very energetic photons. And to the right, the wavelengths get longer and longer until we finally have very, very, very long meters to kilometer wavelengths. I apologize for my fooling around. Normally I would push the buttons on my keyboard, but those don't seem to work through Zoom. So here's KGNU, if that's a favorite station of yours. That's about the wavelength it broadcasts in. Those are photons. I changed. Did anybody see it change? I don't know. But anyway, I hope you saw a spectrum show up in the middle of that near the visible. And I ask you, and you have no way of telling me. But anyway, hopefully that showed up. I'm going to go back to the little arrows. Yeah, I don't know. So let's see. Okay, so to the left of that spectrum that goes red to blues, to the left of that, the photons have more and more energy. They have enough energy then to break molecular bonds, to ionize gases, to interfere with our DNA and cell structure. They're very, very harmful. And luckily, then, if I can somehow advance the slide, everybody's getting dizzy watching the arrow go around. So what this represents then is our atmosphere. And our atmosphere lies over us and protects us from the radiation coming in at all these harmful bands. And this is what we're going to keep going to. Now, that whole spectrum, you could use a lot of different objects to excite it and to make photons of those various wavelengths. The sun basically puts out all of those wavelengths, from the very shortest, very most energetic X-rays, all the way out to radio wavelengths. But 99.9% of those are in the very center of the plot up here. So here's what we would do. We would take the light from anything, from any object, pass it through something that can diffract the light. This is a prism which refracts light. The light goes, depending on the wavelength or color, it goes at different speeds through the glass, and so it breaks up into a spectrum. So this could be our first spectrometer. We could make a little light bulb or something over here to the left that has hydrogen in it. And so then we could stimulate the hydrogen with an arc or something. Now it's emitting radiation. That light goes through our prism, and now the spectrum that you see on the right would look like what you have at the bottom. A whole set of lines, this very beautiful set of hydrogen emission lines. This is something, of course, that was known and discovered late in the 19th century. They used classical physics to try to describe where this came from and couldn't, and had to resort and develop quantum physics to describe this, how the hydrogen atom works and how the energy levels in it are quantized. So here's another thing we could send through that, and this is sending the sunlight through that prism. And if you do that, you get this yellow curve, approximately this yellow curve. Actually, this yellow curve is a black body, a body that has emissivity from its surface as though it was black. It would emit radiation as the yellow curve. And this is a close approximation to what the sun does. You say yes, but you said it does all wavelengths, and it looks like it goes down to 0 here off to the side. Actually, it doesn't. It goes to very, very low numbers, but that's why I say the emission outside of this band here that I show is very, very weak. And then this is roughly the sensitivity of your eye. Now here is another black body then, and this one is for a black body at a temperature of 279 kelvins. Neither of these should have degrees on them, but anyway, they do. And what are kelvins? Well, the degree is the same size as a centigrade degree, but you know, 0 degrees centigrade is where water freezes. If you go colder than that, you can get finally to minus 273 degrees Celsius. And that's called absolute 0. You don't go any colder than that. So somebody said, why don't we just start the scale there at absolute 0 and just call those kelvins? So 279 kelvins, you subtract 273 is about 6 degrees centigrade. And I make one of these curves yellow and one red, and we will be coming back to that shortly. But now let's pick up the sun and the earth, and I've lost my arrow again. Somebody tell me if you see my arrow floating around. Everybody's getting dizzy. I don't know. Well, there, I just did the slides change? I don't know. I didn't push the arrow. So this is just a little schematic. There's the sun, radiation going toward the earth. This is completely out of scale. The earth is about, in physical dimension, about 1/100th of the size of the sun. So the earth So there's my arrow. The Earth is probably about the size of one of these little dots, these little sunspots. But nevertheless, this is just to give us an impression. So the radiation is going from the sun. At the top of the Earth's atmosphere, it's 1362 watts per square meter. It takes that radiation, I'm sorry, TSI stands for total solar radiance, so that's all the light coming from the sun. To cover the distance from the sun to the Earth takes about 8 minutes. The sun, of course, only illuminates the one side of the Earth and dumps tremendous amount of energy. If you take 1362 watts and multiply by a cross section of that hemisphere of the Earth, it's an unbelievable amount of energy. If Excel was selling it for 10 cents a kilowatt hour in a day, it's trillions of dollars worth of energy. And of course, Excel can't do that. They don't have a way to distribute it, nor is there a market for that much. But the Earth uses it. The Earth takes that radiation, warms the ocean, warms the land. You see the clouds, the atmosphere, it moves it around, causes the ocean currents, basically energizes the entire Earth. Couple other little bits of energy, but almost all from the sun. And let me see what I'm supposed to do before I go too much further. I don't know. We'll just see what happens. There, I clicked it again. Okay, so what I was going to ask in that last slide is, does the sun cause the climate of the Earth? And it's a little hesitant, but absolutely it does. The climate that we have, liquid water, clouds, atmosphere moving around, all of that is entirely caused by the sun, I would say. The real question now, though, is climate change. The climate is changing, the climate is warming. Is that change caused by the sun? And that's what we are set out to try to understand. And the way we do that is try to understand how much the sun changes or varies, and then in turn, how much could that affect climate? And climate, when I was in Boulder, Kathy Sabin on Channel 9 Evening News, 5 o'clock, 6 o'clock, 9 o'clock, 10 o'clock, told us the weather, low temperature, high temperature, wind speed, wind direction, precipitation, cloud cover. That was all the weather for the day. And what you do is you take that and you average it over 30 years. And now you have a measure of what climate is in Denver, for example. So you'll hear people say, oh, you know, the last week has been the coldest on record. This global warming is nonsense. No, that's weather, that's not climate, and that's not global warming. So you've got to average it over 30 years. But that's a little aside. I'm going to click again. Somebody's got to tell me if these don't change. So this is when you go into a gas station or something, buy bubble gum, you get baseball cards. These are astrophysical baseball cards. You have a nice picture on the front of our star on the right and our planet on the left. And then when you flip these cards over, you get the statistics. And so for the sun, its age is 4.6 billion years with a capital B. The Earth is 4.5 billion years. You say, well, they're almost the same age. Well, they're almost the same age if you don't count for 100 million years. The sun, it took it a while to get up and get going. It had 100 million years head start, I guess. The rest of these numbers, you don't have to follow them all. The density, you know, we used to always think of density as grams per cubic centimeter, but anyway, this is about 5 grams per cubic centimeter. The composition of the Earth is primarily iron, oxygen, and silicon, so that's all about correct. The density of the Earth going in toward the core gets hotter, but the density doesn't change by tremendous factors. The sun, on the other hand, is quite different. As we said, it's 100 times larger in radius, which makes it 1 million times, over 1 million times in volume, but its mass is only 300,000 times. So what that means is the sun has a density about 1/3 average of what the Earth does, but it's just this large ball of gas, primarily hydrogen, that's collapsing on itself gravitationally it's very, very low density out at the surface, and even halfway into the sun, it's only about the density of water. It's only when you get in the real core that the density shoots up way over anything we have on Earth. And the temperature shoots way up to roughly 16 million kelvins. So the density in the center is very high, the temperature is very high, and that leads to fusion, this source of energy we wish we knew how to do down here on Earth. And I'm not going to spend a whole lot of time on the interior of the sun. The High Altitude Observatory up there at NCAR, I'm hoping they have public lectures from time to time, and you can learn all about the internal structure of the sun. But it's in that core that the hydrogen is, I'm going to say, burned. By that, it isn't a chemical burning, it's a fusion that turns it into helium and releases a tremendous amount of energy. Now, the sun in that shape would be quite stable. After all, it's been going like that for 4.6 billion years. But then the sun has this other difficulty, and that is that it rotates. And being a large ball of gas, as it tries to rotate, it's rotating faster at the equator than it is as you go toward the poles. It's also, because it's a lot of charge that's swirling around, it's trying to generate magnetic fields, but the field lines keep getting twisted and tied up in knots by this differential rotation. This is a very simplistic view that I'm giving you, but it's that magnetic fields tied in knots that's giving rise to the activity on the sun. And this shows up, and then it goes quiet, and then it shows up and it goes quiet, and it goes through an 11-year cycle. So back to whether the sun is changing and varying, it certainly is in these magnetic features on the sun. And we'll see more of this as we go along. But I think now we want to go back to the Earth. And now we'll see what happens to the sunlight when it comes into the Earth. Now, this is a radiative balance diagram. This is from Jeffrey Keel, who I think is a director of one of the climate divisions up at NCAR. Again, hopefully you can find a public lecture where he will explain some of this to you. But the yellow coming in here in the center and the top, this is the incoming solar radiation. It comes in, roughly half of it gets down and is absorbed by the surface of the Earth. Roughly, a tenth of it or so is reflected at the surface, and about a fifth is reflected by the atmosphere. So what you have reflected back out is about a third of what comes in. This outgoing radiation, that's in that first picture we saw of the Earth. The fact that you can see it is this outgoing radiation, and that's called the albedo of the Earth, and it's roughly 1/3. And then there's also here about 20% or so that's being absorbed by the atmosphere. So that would happen, and the sun could keep warming the Earth and warming the Earth and warming the Earth. It would get hotter and hotter. But then, as we saw in the black body diagrams, the Earth gets up to a certain temperature, and now it's radiating in the infrared. And so that's the red diagram over here. It's trying to radiate 390 because that's how warm it is, 390 watts per square meter. But only 235 is really getting out. And what's happening is this is being recycled down here by greenhouse gases. And greenhouse gases are gases in the atmosphere. They need to be triatomic gases. So O2 and N2 are not greenhouse gases, but ozone, O3, water vapor, H2O, these are all triatomic gases, and including, and maybe most important, CO2, act as greenhouse gases. They can absorb this long wavelength radiation and radiate it back to the Earth. So it kind of is going in its own little cycle down here, but only 235 watts is escaping. Now, I went to the website, and Jeff Keel continues to do this type of work, and he has a more recent diagram, but unfortunately, instead of red, he uses beige now, and that just wouldn't fit with my diagram. So I'm sure he's tweaked these numbers slightly, but basically this is the view of how it works. So here's another diagram of that. Coming in on the right side is the solar radiation, the forcing in watts per square meter. And if the Earth was a black sphere, a black body, then the temperature, you follow the red dash line, and the temperature you would get is about 279 kelvins. So that's about 6 degrees. And so what I have to do here is put some water in, because this is going to be important to us. You know, we want the Earth to be in a habitable zone so that water is in a liquid form. And so this drawing shows water, and the red curve is in that. It means that the Earth would have liquid water. Now, this water thing, of course, doesn't stop at 290. You get into hot water if you go way to the right. But the Earth isn't black like that. The Earth has that 30% albedo, which drops it down to here. So the Earth with its albedo, if that's all we had going on, and we could do that, would be extremely cold. All the water would be frozen. We would be way down here at 253 kelvins. But the greenhouse gases shoot it back up so that now we're at 288. And this is where we are because of greenhouse gases. And what we want to know is if we don't want to keep adding more greenhouse gases and keep warming this. Now, you know, over a million years, it'll probably be fine. It's just that over the next 100 years, we don't want to move this temperature dramatically. Why don't we want to do that? Because we've settled in at this temperature, and not only ourselves, but all, whether it goes down to bacteria or COVID or whatever, probably doesn't want to have a big difference in temperature. That was just a poor attempt at a joke. Okay, so here's the spectrum then. The black curve is the spectrum of the sun at the top of the atmosphere. So if we get an instrument up into space at the top of the atmosphere, that's what it would measure. And you'll say, well, that doesn't look like the haystack, that very symmetric yellow thing that you showed. Well, it really is, because the yellow thing that I showed, the wavelength was on a log plot, and this is a linear plot. So it's just a different way of plotting it. But actually that the slope of the sun, the black line going off to the right, matches a black body at 57, 70 degrees or kelvins quite well. And then the spectrum seems to get all chewed up, and that's because of all the atoms primarily in the solar atmosphere and just outside the sun. So the black spectrum comes pushing down through our atmosphere, and at the surface of the Earth, it becomes the red spectrum. And there you see that quite a bit reduced. I don't know what that would look like now with all the smoke in the atmosphere, maybe even reduce more. We have these strong water vapor absorption lines going out into the infrared. But very important, if you look here at 300 nanometers, the red curve just dies. And everything short of that is gone, and that's due to ozone in the atmosphere. So that's this very important thing. This is the region of what they call UVC, B, and A. And this is, it's very important to all of us that this is gone, that the ozone is absorbed that. And now, if you take that spectrum and push it down into the ocean 10 meters down, you find the blue curve. And here I will put approximately the response of your eye. It's very interesting, of course, that the eye has evolved to where it's mostly sensitive to what's coming down at the surface. And you probably know if you go 10 meters down in the ocean, that what you see are primarily blues and greens. So that's how the atmosphere and ocean are processing the spectrum from the sun. Now, moving right along, and probably not quite fast enough, we'll go to variability of the sun. This is a diagram of the sun drawn in 1613. So shortly after the development and invention of the telescope. I don't think this was done by Galileo, but it's a very nice drawing of the sun. And people then take all these records and put them together and come up with a sunspot number. It's just not simply the number. There's a formula to it that has to do with the groups of sunspots and the number of sunspots. And they plot that versus time. Early on, there weren't so many observations. Those are the red X's. But then In about 1750, it became a very good record. I think it's the longest, what I would call climate record, because it's a measurement of a climate variable, and it's made by people who daily went out and dutifully did their job and measured the sun. So this is a record then of solar variability. You see this very striking 11-year cycle of the sun. The other interesting thing is this Maunder minimum back here in 1650 to 1700, where there were almost no sunspots. And I'm sure there were many children who were very disappointed on Christmas morning when they got a telescope and they went out and they couldn't see any sunspots. They probably thought they were an error of some sort, but indeed they came back. And of course, as we move forward measuring the sun, we're always aware and alerted, and or we should be aware of another period of this sort coming. And now I want to bring in Jack Eddy. Jack Eddy was a solar scientist at the High Altitude Observatory. Then he worked for NASA. Jack was a true gentleman, a wonderful man. He inspired us a lot on our way, and he was always very supportive of the work that we were doing. And I'd like to do a shout out to Jack. So now I'll bring it to the beginning of our program. I showed up here in here I'm in Durango now. I keep thinking I'm in Boulder. I showed up in Boulder in 1972. One of my mentors at Johns Hopkins was Bill Fasty, and he had an experiment on Apollo 17 that launched in December of 1972. So he was going to have his instrument at the moon, not on the surface, but in the orbiter, and trying to look for a residual atmosphere, and he needed a measurement of the sun. Well, I had just shown up at LASP, and I had procured a small spectrometer, and I could get it on a rocket. And so I flew that and got this spectrum of the sun. And this was the first spectrum I got. Actually, the top one isn't the first. The instrument continues to scan, and there were about 20 of these obtained above the atmosphere. And I think the top one is probably the last one, while it was still above 100 kilometers or so. But now the rocket is coming down. You see a big chunk of this absorbed away. The next scan, an even bigger chunk is absorbed away. And so this was my first introduction to the absorption of solar spectrum by the Earth. This is absorption by O2, molecular oxygen, and that becomes a source of ozone in the atmosphere. And so as I got back to the university, I met Dr. Julius London of the Astrogeophysics department. And Julie and I became great friends. He had a lot of patience, and over the years, he tried to instruct me about what was going on in the middle atmosphere. And Julie and I worked very closely. He was co-investigator on all the missions I conducted up to and including SORCE. So there's a shout out for Julie London. And now here's a couple other folks. These Sherry Rowland and Mario Molina are chemists in California. So now we're moving forward to 1974, and they wrote a paper that said that freons being released in the atmosphere were destroying ozone, and that would be very, very bad. So we had to study and understand ozone in the atmosphere. So Charles Barth, who was director of LASP, together with some folks, certainly in LASP at the university, Julie London, put together a proposal and launched the SME satellite. The proposal was written in about 1975, and it was launched in 1981. It operated for 9 years. And not to be surprised, I think I'm running out of time, so I'm going to need to move along a little bit. But that was SME. We worked on that. You can see in the bottom here, one of the lines of SME measured during its mission. You can see us going from pretty maximum solar activity through a minimum and back to a maximum. And now I'm going to see how I can move along. So NASA decided they wanted to do their own ozone satellite, and they called it the Upper Atmosphere Research Satellite. They put out an announcement of opportunity, and I wrote a proposal to build an instrument called SOLSTICE. And we started off building that instrument. Now this is UARS, gigantic spacecraft, filled the space or the whole shuttle bay, launched in 1991. Our instrument is out here in this solar platform. I don't know if you can see my arrow trying to point at it. But the other fortuitous thing that happened at this time, actually we're not quite there yet. This isn't going to launch till 1991. But Tom Woods, and I apologize, this is not a great picture, but it's what I can get off the LASP website. Maybe the LASP website needs to get a more higher resolution pictures. Anyway, Tom Woods joined us in 1987, worked on getting the UARS instrument into orbit, set off on his own in extreme ultraviolet observations of the sun, but continued to work with us. And as you know, then Tom, when I left LASP, he became the principal investigator, and actually he ran SORCE longer than I did, at least in orbit. I'm going to move quickly here because this is a talk, or this piece here is about the SOLSTICE instrument, and I think maybe I could be invited back to give another lecture sometime. But the SOLSTICE idea is you look at the sun using the very same instrument. By that I mean the optics and detector. You look at bright blue stars, and so what you're doing is comparing the sun to these bright blue stars. And the only difficulty you have is shown here, that the sun is about 10 to the 12th times brighter than the stars. But nevertheless, we make an instrument and we do this. Here again is Bill Fasty, this mentor that I had from Johns Hopkins University, I really think it was his idea. He's the one that kept pushing me to make this happen. And all I'm going to, never mind, I'm going to skip this. Now I'm going to jump to EOS, the Earth Observing System. So now we're way, way forward, I guess, but UARS still hasn't launched. It hasn't launched, and NASA now really wants to do something big, and Ronald Reagan signs this new start for the Space Station Freedom. Space Station Freedom will be in a low Earth orbit, not a low Earth orbit, low inclination orbit, and all the atmospheric people, earth science people, oceanographers people want to be in a polar orbit. So part of Space Station Freedom was System Z, which would be these large polar platforms. So NASA put out an announcement of opportunity. 458 proposals were received, 30 instruments were selected, and we were one. And what we proposed, Tom Woods and I, was a SOLSTICE instrument, and that got selected. And so here's all the things System Z wanted to do. You can see clouds, you can see ocean, you can see surface structure, you can see snow, but one of the things is solar radiation. So we jumped in, we were selected, and here's a whole set of things on EOS, and the final bullet says that, yes, SOLSTICE was going to look at the sun. They don't need it to be on a polar platform. It could be on the big space station. They kept wanting us to be on space station, but they said, you just sit over here on the side. You're going to be a flight of opportunity. And flight of opportunity was foo. So we were a foo for quite a few years, had a lot of patience. But in the meantime, of course, we got SOLSTICE up. And so now here is SOLSTICE. This is the UARS SOLSTICE, and it's looking at this whole set of stars, looking at the sun in between. There's no solar measurements here. These are only the stars. And because all of those stars fit on that curve, I think it's undeniable that that's the degradation of the instrument. So over almost 8 years, the instrument degraded about 22%. And I must tell you, that's not a lot for solar instruments. The most harmful thing you can do if you build a wonderful instrument is launch it and point it at the sun, because the sun has extremely rough and dangerous radiation going in your instrument. And typically, solar instruments have a lot of trouble with that. So these stars seem to track that very well. Well, and so EOS, we're building instruments. We're busy building instruments, and this is the EOS SOLSTICE version of that. So it's going to look at stars in the sun. Again, you can tell I'm rushing through this, rush, rush, rush. But one of the things that we found is that The stars worked great at the short wavelength because you could do this star comparison to about 1% and track what the instrument was doing to about 1%. And at those short wavelength, the sun was varying by maybe 40, 50%. So that knowing your instrument to 1% and measuring 40, 50 isn't bad. When we got out above 300 nanometers, the sun was varying probably far less than 1%. And the stars were even getting worse because now we really did have 12 orders of magnitude different brightness. So we were having trouble 300 nanometers long. And so I decided that we needed a different concept for that. Now, I remind you, we were accepted. We were just a foo. We were not supposed to be doing anything outrageous like changing instruments, but nevertheless we did. So I went to, I'm gonna kind of scan down through this. And I hope you people out there know you can move me around, move me off the view graph if I'm there. So this is the concept, and this is being used by an Acrim instrument built by JPL, also used by a European instrument. It was the best way to measure radiation if you want to do that, the best absolute way to do it. And here's how you do it. You make these metal cones, preferably maybe make them out of silver, which is a very good heat conductor. You make them very, very black on the inside. What Acrim did is they painted them black, but anyway, they're very black on the inside. You wind a wire on the outside, a heater wire, and you run that off and you can provide current to that and heat it up. And you put a thermistor on it. And then over to the right, you have these very sophisticated electronics, and all they're trying to do is keep those two thermistors, those two cones at the very same temperature. And it's just blind. It's in a different room. It's running along and it's keeping the temperature constant between the two. And then what you do is you open this shutter in front of one of those cones and you let sunlight in. So now total solar radiance enters the cone. Of course, it gets absorbed in there and it starts heating it. So the electronics, they don't know that you did this. So what they do is they have to cut the current to this heater to keep these balanced. And how much should they cut it? They should cut it by precisely the number of watts that came in this aperture. So this is a very significant and good way to do this. So I searched the halls of LASP and found my good friend, George Lawrence, and told him we needed to make a spectrometer that had this type of detector, that is an absolute detector. So George, is the genius in LASP, he came up with this concept. And what this is a little piece here of diamond, not VS2 diamond joules, but CVD diamond, which is chemically vapor deposited diamond. It's a little strip of diamond, which is a very good thermal conductor. It has a little heater on the back and it has thermistors. You hang this little thing, which is about the size of a piece of lead in one of these mechanical pen or pencil type things. And it hangs in here on Kapton strands. So it's just isolated. And there's actually two of these. They're in this thermal housing. One of them is facing the other direction. Only one of them, when light comes in this slit, will get light on it. So you do the same thing as the active cavity radiometer that I just showed you. You open the slit here and let some light in. The light comes in, gets refracted by this prism back here to this detector. And when the shutter's open, you find that you have to reduce the current, the heat in this one by precisely the amount of now milliwatts or even microwatts corresponding to the light. So we built this instrument. That's going great. I think my time is almost up. And there's a picture of George Lawrence. So a shout out to George, who did a great job with this. And this is a picture of the instrument. It's a beautiful piece of work. Jerry Harder became the instrument scientist on that, and maybe sometime he will give a talk about the results from that. And then Tom Woods had an instrument that does X-rays called the XPS, the X-ray photometer system. And I'm just racing along here. So Then a thing happened that was strange. One more announcement of opportunity, and this will be the last one. NASA decided they needed a follow-on. They had an Acrom flying, and they needed a follow-on to that. And so they put out an announcement of opportunity for someone to build that. JPL had been building these since 1978, so they should have had a shoe-in to get to win this. But nevertheless, for various reasons, I won't go into all the politics, we decided we needed to propose this. So I went to George Lawrence and I said, George, can we build an instrument like Ackerman? Don't make any major changes to it. They'll never accept that. And George went off and thought about it. And then he came back and he said, yeah, but we sure don't want to do it the way they do it. We can do it much better. Their cones have paint, and we're going to use this etched nickel, this nickel phosphide, much better black absorber, no organics, much better than paint. We'll use that. That's much better. Number two, they do the optics wrong. The optic, the first thing is an aperture, and they have the aperture way back in front of the detector. George said it's got to be out front. And then the third thing George said is this has to be phase sensitive detection. In other words, the shutter will open and close in a very periodic fashion. And when we analyze the data, we will do phase sensitive detection at that shutter frequency. You can tell I'm doing this very quickly. Well, we then went to defend the proposal. And I'll tell you, the people at NIST, the people that knew radiometry were overwhelmed by what George had done. This was a fantastic advance, and this instrument now becomes a state of the art. Let me just now show what the state of, or what had been done before that in measuring TSI. These are all measurements, and you can see they're all at the same time, but they differ significantly, and that's due to the absolute calibration of them. There's something that's not accounted for. Most of them seem to be high, which would indicate scattered light. And then here are the more recent ones, and they're getting much better. The Virgo is a European one. This is this Acrom 3 that we were going to replace. And now we launch SORCE with this new instrument. And where do you think it'll come in? Boy, we wish it could come in right in there, but it came in down there. And mind you, Greg Kopp is in charge of this, but he and George Lawrence know their numbers, and they kept checking it and saying, yes, this is the correct value, these are wrong. You don't do this by a vote. You've got to convince these people that their numbers are high. But special facility was built at LASP. Special work was done. These instruments, not these instruments, are in orbit, but second versions of them came to LASP when were measured. And indeed, finally, everything was reconciled and came together with Tim. So there's so many great advances that SORCE has made. You know, originally I was to give this talk in April, and really originally I think Tom Woods was to give the talk, but he's such a busy person that he couldn't give it in April. So I got called upon, and now I'm doing the webinar, but still there's plenty of room for Tom Woods and any of the scientists on SORCE to come and give additional talks. And now I'm going to end with this. This is some special people. This is special people way back in probably, I think even before the launch. And these were the people that at least at that day at work were working on SORCE. Just as many special people like this have continued to contribute to SORCE all the way up to 2020, and maybe many more than this. I would point out this individual here. You can see the arrow. This is Tom Sparn. He was the program manager, and he did all the work while we were waiting in the wings as a foo. And maybe if there's LASP people watching this, they recognize themselves. Here's Greg Kopp. Here's a younger version of myself. Oops, I'm sorry, I didn't mean to do that. Shouldn't have clicked on myself. And then here's Tom Woods and all the other people, LASP people who contributed so much to the success of this. And since I did jump ahead to that last one, this is that same view graph I've shown, but now Greg Kopp has gotten everybody in line, and this is now the record of TSI with the SOLSTICE or the SORCE instrument here in red, and you can see how that's in phase with the sunspot number, et cetera, et cetera. And I'm done, and listen, please don't clap because I won't hear you. Anyway, thank you very much, and I'm sorry to rush this at the end, and I'm sorry to have passed over so much. So, I'm done. Hello, Amy.
Okay, thank you, Gary. If anybody has any questions, feel free to use the question and answer button at the bottom of the Zoom window.
And if you don't come in with questions, I'm going to keep talking.
Oh, there's some questions that just came in. Okay, so we have,
Did you ask him to do just true and false?
yeah. Okay, so a question from Tom Woods. Thanks, Gary. The time from the EOS proposal to SORCE launch took 14 years. As overlapping missions are important for solar irradiance climate records, what are your ideas for NASA to reduce the time for new mission development?
Well, with SORCE, so much of that time we were doing very, very little, except studying this and studying that. I mean, they never really came forward with the money for us to go. SORCE had some very sophisticated development, and especially, for example, changing that one channel SOLSTICE to the SIM instrument, that would take some time. But if we had really had the go-ahead in '89, I think we could have been ready to launch in 5 years. As a matter of fact, that might have been what we originally proposed. But I think it's just not the initial acceptance of a proposal and then the funding of it. And I assume that Tom Woods has some ideas of what could be done. Things have changed so much. The SME, we probably developed that whole spacecraft. Ball Brothers built the spacecraft and we built the instruments, but probably beginning to end, 4 years at the most. And it wasn't a tremendously sophisticated, but once we got going on SORCE with orbital, it didn't take us that long. I don't know, maybe 5 years. Tom Sparn would probably better know that. We just waited in the eaves for so long without getting a real start.
Okay, so the next question is, it's kind of a two-part, well, actually not, but somebody wants to know how the age of the sun is measured.
Yeah, that's a good question. That's a good HAO question.
Yeah.
I think it's measured from models. One of the stars I was going to talk about is Eta Ursa Majoris, Eta in the Big Bear, which is the end of the handle. That's a star that's 17,000 kelvins, and it's 10 billion years. So I believe that all of these ages are known by, and again, you need to ask an HAO person, I think, but I think it's by the model, by the mass that they have and how much they're burning and how fast they're burning. And yeah, but I'm not the one probably to answer that question. And nor do I really know the Earth number, 4.5 billion years. I think the geologists probably come up with that, but I don't.
Somebody wants to know how the number of sunspots affects our climate.
Well, I don't really have, I didn't bring one, but the sunspots are dark and they really are a depression in the light from the sun. And so if there were only sunspots, the sun would be darker and quieter when it was more active, but they're compensated by the surrounding plage or bright region, and more than compensated by it. And I'm trying to think if, I don't think I did that. But anyway, they're very good models. Judith Lean, Greg Kopp can certainly answer that, but where they come up with the sunspot blocking, but then adding in the facular brightening. And indeed, when there are more sunspots, there are more bright faculae, and indeed the sun is brighter at that time, and that's the solar maximum. I don't know if that answered the question, did it?
Yep, I think that that was a good answer. So this is a question more pertaining to instrumentation. What was the reason for the phase sensitive detection? Why was that an improvement to what was previously done?
Well, I think people, you know, like George Lawrence and no electronics know that, but there's a lot of noise. As a matter of fact, Greg Kopp must be there in the audience, and he can certainly answer that. But the phase sensitive detection, there's a lot of noise in the detector, and so there's noise in there, but it's not at the phase of the shutter. What's at the phase of the shutter is only the signal from the sun, and so somehow when you do that phase sensitive detection, you make a serious limitation on the amount of noise that's coming through in your detection. And Greg Kopp, just nod or put a thumbs up or something if you agree with that. And I wish that George Lawrence was here because he would have a very succinct answer. But I think phase sensitive detection is used widely in electrical engineering. And a matter of fact, all the optical people, when George Lawrence came forward with that, kind of just knocked their head and said, why didn't we think about that? We've been doing this for years. That's the most obvious thing, but we never thought about it. And I think that points out why it's very valuable to bring people from other disciplines into whatever you're studying, because they bring a whole different insight into it, and they apply completely new dramatic techniques.
So there's one more question. A comment from Greg Kopp that said,
Yeah,
good
there he
answer
is.
on PSD. So he gave you the thumbs up. There's a question about that you said photons were not affected by gravity, and they wanted to know how that could be.
Well, I say that photons have no mass, and so they're not directly affected by gravity. But of course, Einstein's theory of general relativity says that light bends when it goes around, for example, the sun. You know, some of the early proofs of general relativity were eclipse observations of stars behind the sun. You observe them, 6 months ahead of time, and then during the eclipse, and indeed they've been moved. But it's a question of whether the gravity really affected the photon or whether it really bent or warped time-space. And so then that becomes a thing of general relativity. But I just mean that in classical things like the photons entering our atmosphere and buzzing around here, they're not affected by gravity.
Okay, so that's all of our questions, unless anybody wants to type in another one real quick. You got comments saying that you did a great job, Gary, and that even though you were rushed, it was very easy to follow and well done. So
well, I'm going to tell you, because you need to know this. I mean, doing these webinars or doing anything virtual like this, it is very hard for me to give a talk like this when I can't see the audience. I mean, and that's what you're limited by. But when I give a talk, you're looking at the audience and you're looking for people having puzzled looks. They're just not getting it. What you're saying is either not right or it's going over their head. And when you don't see anyone, it's very difficult. And then you might as well just do a recording But the nice thing about a recording, if you did it, is you get to then edit it and go over it 3 or 4 times to straighten it out. And yeah, this is difficult. And yeah, I appreciate everybody who came tonight and who listened, because it's probably a little difficult to be out on the attendee side as well. We'll learn. You know, 10 years ago, we wouldn't have been doing this. It would have been COVID is here. The last public lectures are canceled, period, the end. But now we can do this, and maybe we're going to get much better at doing this.
Yeah, well, I think it was a success for our first time, and I thought you were a great guinea pig for us, and you did great. We could see everything you were doing, and so we just really appreciate it.
Thumbs up, Gary. Thank you very much.
All right. All right. Well, thank you. I appreciate being invited, and I always like to share what I know with LASP people and whoever else is in the audience. I'm not prejudiced.